Well, welcome back, everybody. It's hard to believe another week has gone by, and you guys are probably like, "It's Friday. Let's get the heck out of here. It's time to enjoy the weekend." Well, um, anyways, what I want to do this morning is we're gonna go over the quiz that you guys had for homework for last week, and then what we'll do is we're going to talk about sieving. And obviously, if at any point you guys have any questions or anything, please feel free to unmute yourself and ask questions. The more interaction, the more questions, the more interesting it is for everybody. So we want to make sure that you feel like you can jump in at any time because you're not going to interrupt us, you're not going to offend us, you're not going to anything. We've pretty much experienced everything you can imagine in doing these trainings for people over the years. So nothing you ask will be a shocker or surprise. So, okay, so hopefully you can see the quiz from last week. So I'm just going to go through the answers, and if anybody has any questions about it, I'm happy to answer them, and then we will jump into the new material. So the first question, the asphalt industry is responsible for aggregate production, asphalt paving mixtures, placement of asphalt pavements, pavement maintenance, or all of the above. Hopefully you all chose all of the above because they are responsible for all of those things. So there's a large scale of things that they deal with, all the way from the rock all the way to maintaining the pavement after it's placed. Number two, hot mix asphalt pavements need to be landfilled at the end of their service life as it's not a recyclable material. That is false. Asphalt is essentially 100% recyclable. So we can reuse this material over and over again, and it's obviously environmentally friendly and beneficial economically. So there are benefits all the way around to that. So number two is false because we can reuse all of that material. Number three, maintaining our infrastructure is vital to our economy because the economy is dependent upon quality infrastructure. Quality infrastructure promotes safety, both of those, or none of the above. And the correct answer was both of those, both A and B, because the economy is dependent upon having infrastructure that is usable and can be freely traveled, as well as promoting safety. Number four, HMA is produced by spraying asphalt onto a stockpile of rocks and sand in the roadway. No, that's not correct. How about injecting asphalt into a stone quarry wall? No, we're not doing that. Mixing stone, sand, and rocks in a cement mixer mounted on a truck. That is incorrect. The correct answer is D, mixing hot liquid asphalt with stone and sand at the production facility. So that's where HMA is produced, at a central facility, and we inject hot liquid asphalt onto heated stone and sand, and that's how we get asphalt. Number five, approximately blank percent of the HMA mixture is comprised of liquid asphalt. It's around 5%. So the right answer here would have been B, 5%. MTV, what does it stand for? Well, it's not music TV. It stands for material transfer vehicle. So we're not talking about Jers Days or whatever it is that they do on, on MTV. I've never been completely clear on that. I see the ads on TV, but I never know what it stands for. How about number seven? Tack is applied to the roadway to A, heat the surface. Nope, doesn't do that. B, rejuvenate the base layer. Nope, doesn't do that. Keeps the interface slippery. No, we want to glue those layers together. So the correct answer is D, bond the new pavement to the surface. We want to glue it all together so it acts as a single piece of material. Even though you're only putting 2 inches down, but you're gluing it down to the other 8 inches that are there, so it all acts as a single piece of material. Number 8, HMA is spread out to the paver screed via the use of blank on the paver. Nozzles? No. Springs? No. Augers? Yep, that's how it moves that material out from along the paver. So that was the correct answer is C for number 8. Number 9, quality control is intended to exercise superiority over the paving crew. No, that's not what they're there for. Ensure HMA meets quality and specification requirements. Ding, 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 ding. We have a winner at B. That is the correct answer. So quality control is really out there to work with everybody to ensure that the material is meeting quality and it is actually hitting the specification requirements. Number 10, The two primary categories of pavement distress are environmental and traffic loading. Bing, we have an answer at A. That is our right answer. The other things are not true. How about, and number 11, when water freezes, A, it thaws very quickly. Well, it depends on the temperature on that one, so I wouldn't accept that one. Does water shrink when it freezes? Nope, it does not. It actually expands. So the right answer is C. Number 12, thermal cycling describes the freezing and thawing of pavement structure as a result of climate patterns. That is false. Thermal cycling occurs every time the sun shines on the pavement. It warms up and it expands a little bit. And then when the sun goes down, it tries to contract, and it can't do that because the sand and the stone help to keep it apart a little bit because of the friction from that. And so it can't pull back together to the same shape it was the night before. So it gets a little bit thicker every day. That's known as thermal cycling, and that causes cracking in the pavement. Number 13, quality control technicians sample and test paving materials. Yep, I like that one. Observe delivery condition of the HMA. That is true. And observe placement and compaction. That is true. So the right answer to number 13 is all of the above. Number 14, reflective stripping or rutting, stripping, fatigue cracking are all examples of a defective MTV device? No, that's not correct. Pavement distresses, that is correct. So those are examples of pavement distresses. And number 15, rutting is the result of freezing and thawing of the pavement. That is false. Rutting is actually caused because the asphalt binder is not strong enough to hold everything together. And when it warms up, it gets soft in the wheel paths, and then you drive over it and it just squishes that material out. And so you get depressions in the wheel paths where water collects, and where that water collects, it creates a safety hazard and it is difficult to remove the snow and ice from those areas. So that is the quiz from yesterday, or from last week rather. Anybody have any questions on any of those on those questions? Questions on the questions? If not, we're going to jump into sieve analysis, or talking about sieving of materials, to look at the different sizes of the materials in there. Okay. So here we go. We are on session number 2. So we said that the asphalt industry is responsible for aggregate production. And so today we're going to talk about those aggregates and how they're made and how we check to make sure that they meet those requirements, because we need to make sure we have the right size of all the particles in there so that they lock together tightly so that the roadway can be compacted and it can support the load that is going to be applied to it. Go ahead, Alex. So when you look down on a pavement, really what you're seeing is mostly stone and some sand on the surface. And when it first comes out, it's all jet black. And then what happens is that as the sun bakes on that pavement, the asphalt on the very, very surface of it ages and it falls off. And what you look down on a pavement that's a couple years old, and it looks like all rocks that are in there. That's what you're seeing is all the stone and the sand that's put in there. And now that won't age anymore from ultraviolet light, because that's going to block the sun coming down, because the sun can't go through the rocks and the sand. And so the ultraviolet light only ages the very, very top layer of it. And so during the actual production of this stuff, we're going to heat up the sand and the stone to dry it and heat it up. And then we're going to add the asphalt binder to it, and then we're going to pave the roads with it. And that's how we get our pavement. And so if you look at things by weight, the pavement consists of about 95% sand and stone. About 95% of the weight of the material you see out there is sand and stone. And 5% of it is the black asphalt liquid binder in there. And so the aggregate plays a big part in the way that materials are going to behave, because as that material is out there, it is essentially 95% of it is sand and stone. So that has a huge impact. What we want to make sure, and this is one thing that a QC technician does a lot of, is we want to make sure that we have it's called a gradation when we do it, when we analyze an aggregate to see what sizes are in there. We're looking at the spread of the different sizes, because if I just give you all large pieces and tell you to pack them tightly together with no smaller pieces to fit between, we end up with a lot of void space. We let a lot of empty space where the aggregates just don't lock. There's nothing to fill in those spaces. So when we make our pavements, we want to make sure that we have the right size proportions of all the different material, of all the different sizes, so that the larger pieces fit together and then the smaller pieces fit inside those void spaces, so on and so forth, all the way down through, so that we can minimize a lot of the void space. We also have, over the years, have learned a lot about the aggregates that we use, and we need to make sure that we have the right sizes and the right proportions to resist damage from the actual production. And part of that is we need to make sure the aggregates are strong enough and they're the right size so that they can withstand all the bangs. There's a lot of beating that goes on of our aggregates until it's actually down in the roadway and compacting, because we have 10-ton rollers beating on it. We've got all kinds of different opportunities for the aggregates to degrade. We also need to make sure that they're not going to be susceptible to freeze-thaw damage, because water gets in there and it likes to break the aggregate apart, because it goes into the aggregate, freezes, and then it swells when it freezes. And then it's going to want to push everything apart and break those aggregates apart. It's just like if you have a house and you lose the heat in your house, and it's cold outside, the pipes will freeze and then they'll burst. The reason they burst is because the water gets trapped in those pipes, and then when it wants to freeze, it expands and it actually pops the pipes apart. And that's why you have broken pipes when it's really cold outside, because that water will expand and freeze. Similar thing happens inside aggregates in a pavement. We need to make sure they're strong enough that they won't break apart. We look at rocks and say, hey, they're hard, they got to be strong enough, but there's a lot of rocks out there that can't withstand that kind of distress. We also want to make sure that as we load this thing with traffic, that the aggregates themselves aren't going to break down as well. So aggregates have a lot to do. There's a lot of tests involved in checking our aggregates. Because of our time constraints, we can't go into all of them, but we'll talk about them a little bit. Go ahead, Alex. And now we have to look at the different types of aggregates we have. We have natural aggregates. These are the ones that Mother Nature deposited for us, mostly when the glaciers retreated. And these are dug up from the earth. They're quarries, they're pits, they have a lot of different names. But because they were deposited by the glaciers when they retreated 10,000 years ago, these aggregates were deposited in water. So when things are deposited in water, they tend to tumble. And when they tumble, they tend to become more rounded. And as they become more rounded, they can't support as much load, because it's like if you try to stand on if you've ever been to the beach and the ocean, that is, and you're standing on the dry sand at the ocean, at the beach, and you try to run on that sand just kind of comes out. When you push off, the sand just rolls out from underneath your feet. Whereas if you're, let's say, on a walking path that has sand on it, but it's more of like angular material, when you go to push off of that material doesn't really slide out from underneath your feet. So it's a lot easier to push off of and not have that happen. That's why natural aggregates, we use them, but we don't use a lot of them in our pavements, because we like things to lock together, because the more they're locked together, the easier it is for them to support load when you have traffic on it, so it doesn't just push out of the way. So you may hear the term bank run. That means they're just natural aggregates. And we have a lot of natural aggregates around, but we can't access them nearly as much as we used to be able to, because we built on them and things like that. And so if you just built your dream house and somebody wants to open up a quarry right next to your house, you're not going to be real happy with that. So we shifted and we use a lot more manufactured aggregates. And by manufactured, what we mean is that these are actually stone and sand that we process from ledge. So we drill holes in the ledge, load it with dynamite, blast it off of there, and then we actually run that through crushers to get it down to the size that we're looking for. And so these manufactured aggregates are very angular, because they have literally just been, one day they were part of the ledge, and the next day they're blasted and crushed into a million pieces. And so now they are a very angular material. They tend to be cleaner. There's less dust in there. And so we use a lot of manufactured aggregates, not only because natural aggregates are a little harder to come by, but because of the fact that they are more angular and they lock together better. Go ahead, Alex. And this is just a picture, and you can see the one on the left over here. The one on the left, this is a natural material. That material is kind of rounded. I mean, there's some sharper edges in a few pieces, but in general, it's a lot more rounded. Whereas the stuff over here on the right, this is a manufactured stone, and this is actually from a blast and a crush. And so this is where that material comes from. Go ahead. And these are two sands as well. The one on the left is a natural sand. And again, if you look at those particles, they tend to have more rounded edges. And if you were to walk barefoot across the one on the left, there might be one or two things that make the bottom of your feet hurt. But the one on the right, this is a manufactured sand. This comes out of the crushing process as well. This one over here on the right, if you walk barefoot through that, that's going to hurt. That's because that stuff is much more angular, and it's going to be like little pinpricks on the bottom of your feet. And so this guy over here on the right, that's a manufactured sand. Go ahead, Alex. So just going to give you a second to look at these guys. And based on what we just talked about, I'm going to give you a clue. There are 2 natural sands in here and 3 manufactured sands. How many of you guys want to, who wants to be brave and take a guess at what number 1 is? You can unmute yourself and shout out from the rooftops.
Or you can type it in the chat if that's easier logistically.
We have a guess at Ellis. What is it?
Okay.
2 and 3 and 5, she thinks. No, you only said 2.
2,
5.
2, 3, and 5 are which? Manufactured or natural?
Manufactured.
Okay, I like 2 and 5 for manufactured.
Yep.
3 that's actually a natural sand. How about number 4? When you look at number 4, do you see a lot of angular particles in number 4? Number 4 is manufactured as well. So number 1 and 3 are natural. 2, 4, and 5 are manufactured. Hey,
well, thank you for that, but we're brave guessers here.
Hey,
and I think number 1 kind of looks like the starter concrete, and maybe that's what confused. But anyway, thank you. We learned something good.
No, it's good. Yep, we want to have you guys participate, and let's see. We had one in the chat. Yep, Juan got 3 and 4 is natural. Well, 3 I buy, 4 is manufactured. Granted, it's hard to see from the slide. I'll give you that much. Yep, 3 is definitely manufactured. 3 is natural rather. 4 is manufactured. Number 1 is a natural sand as well. Again, I have that home field advantage. I saw these things once in person, so it makes it a little easier.
Definitely.
Okay, go ahead, Alex. And then we have to talk about how we're going to sample these materials, because if we don't do a good job sampling our aggregates when we go to test them, they don't represent what's out there. And if it doesn't represent what's out there, you're kind of wasting your time. And so you want to make sure that when we sample these things, we do it correctly. And there is a process to try to minimize any influence we may have by accident in making sure that that material is going to represent what's out there. So
this is where I'll take over.
Okay.
So Jim overviewed all the different types of testing we're going to be doing on aggregate to determine whether or not we can even use it to make mix with. And we're going to get into the details of how you actually calculate a gradation. The way we describe aggregate is by the size of the particles in it, all the different sizes, but then because we're characterizing all the different sizes, we have to figure them into percents. So it's a very repetitive process. Don't be alarmed by the math we're about to show you. Once you have the hang of it, you just do it over and over and over and over again. And for someone who's actually running these daily in a plant environment or in a quarry, there are spreadsheets available and forms that get filled out automatically by those spreadsheets. But it is important to know the fundamentals. And, that's why we go through it step by step here. Is there anything else I want to say on this slide? No, I don't think so. All right. The gradation, as Jim mentioned earlier, is also called a sieve analysis. And when we use the term sieve, for anyone who's spent considerable time in a sandbox like I did as a child, you've probably played with something that is technically a sieve. But these are much more scientific instruments when we're using them for design of roadways. So sieves are containers that have openings of specific sizes to separate fractions, which are the percents or a portion of the whole sample. So we can then weigh them individually. And you can see in this picture, there's larger openings here versus there are openings on this. It's smaller than the screens on your windows at your house. So we'll take these sieves and we stack them, putting the largest opening on the top, smallest opening on the bottom, and we finish every sieve stack with a pan. If you don't put a pan in, you make a big mess and you actually ruin your sample. The reason being is when we start and stop this test, when we're done, we want to make sure we have pretty much the same amount of material. Otherwise, we would have lost it somewhere along the way and the test is also invalid. So we're talking about when we say sieve sizes, for the larger stuff, we're going to describe it by the actual measurement. So like a 1/2 inch, a 3/8. But once we start getting smaller, because of the diameter of the wire, we then start just saying the number of openings per inch. So we've got like a number 4 sieve and a number 8. And a number 4 sieve is close to a 1/4 inch, but it's actually not because of the diameter of the wire in that grid. And you'll see a quick video in a couple slides showing you a little clearer some of the opening sizes, but we go all the way down to 200 openings per inch, which is very, very small. It's the smallest we can mechanically separate aggregate particles of sand and stone from themselves. And one of the challenges at that really small size is static electricity actually can hold those small pieces onto the larger stuff. So even though we have this test that we can run, there are some blind spots to it too that we as users of the test have to be aware of. With aggregate testing, most of what you do is wetting and drying aggregate, and it's pretty funny. But to start this test, we're going to dry it out. So we've got what's called a forced draft oven in most of these laboratories, and this is a large oven. Like I could get in there. It's pretty big. And so we've got multiple racks and we put our samples in there. We're going to dry them to a constant mass, meaning the moisture, there's no more moisture in it. So we set the oven slightly above boiling temperature, 230 degrees Fahrenheit or 110 degrees Celsius, right? We don't need it to be 400 degrees. We're just trying to drive the moisture out. And the chances are the hotter it goes, the more likely we might break down an aggregate. I mean, hopefully our aggregate's strong enough, but we assume the worst, right? We don't know about the sample necessarily before we get it. And sometimes we're testing old material that we're doing forensic testing on. So once that aggregate's dry, we're going to weigh it. That's a pretty straightforward step. We put it on a scale. Most labs now have digital scales. So you set your sample in a bowl that has been tiered, meaning the weight of the bowl is either accounted for by you or it's been zeroed out in the scale. You pour your sample in there and you can weigh it. We're going to record that as our starting mass. We then insert the sample through the top of our stack of sieves, and you're going to hear it start trickling down through. But we need to agitate it more to make sure every single particle has made its way down as far as it can go, right? This is basically a method of refusing these shapes to go any further. And the smaller they are, the further they make it. Some of them go all the way down to the pan. Material that's finer than 200, we consider that to be silt and clay or dust. There's also, it's not just silt and clay, but silt and clay, which are problematic types of materials for us in construction, are finer than 200. I got a step ahead of me. So we dump the sample into the top and then what's going on here? Oh, geez. It's trying to buffer this video. So once the sample's in, we have to agitate it. And you actually can manually shake these by hand. It's very tedious. And if that was your job all day, it would not be great. So fortunately, we have machines that can help us with this. The first is called a Rotap, and the other is a cabinet style shaker. Basically, you take your stack of sieves, put it in there, and it's actually going to shake it, rotate it, knock it with a hammer or like a paddle in the case of the Rotap. We're going to show you a video of a cabinet style shaker. That's probably the most common type these days, but the Rotap was the original mechanical shaker of these sieves. So here's a quick video showing you loading a sample in, and I'm going to show you different sizes as well of these sieves. Right, got a sample of aggregate, large opening, smaller, and they just get progressively smaller. Finally, the pan, nothing's going to pass through that. So they were opposite, right? I tipped them up so the largest opening is now at the top. I didn't show putting a lid on there, but hopefully you'll see the lid here when I put it into the cabinet. Those fingers that you saw before we put the sample in, oh yeah, you can see one now. They're actually kind of tapping it as it rotates. It's fairly loud, which is why it has the cabinet. We actually have a separate room where we do all of our noisy things that this happens in. It's going to run for 7 to 10 minutes until a term called sieving thoroughness has been achieved. And at that point, you then need to look at each screen, and we're going to weigh the particles individually on these screens. You can see different amounts of material have been left, right? Every sample is going to be slightly different. In the case of hot mix pavements, we want our samples to be pretty much the same. There's an allowable difference because it is a natural material. It's going to have variability in it, but the question is how much is too much? And we've written that out in specifications as a community, right? As engineers and users of aggregate in the world. So following that agitation, each sieve is cleaned out, as I mentioned, and we're going to weigh it in a pan. What we're going to teach you, there are a couple different ways to do this. You could weigh each sieve individually, or you can do it cumulatively. And by cumulatively, we mean you tear a bowl, you put your largest particles in, write that number down, then you put the next next smaller sieve in, you weigh that, and you're adding into the bowl each time. That's called cumulative. We're going to teach you that method because it's a slightly more straightforward math. Cumulative weighing means that the weight retained for each sieve includes all the aggregate on that sieve and the sieves above it. So the idea here is if you've got a 3/8 inch screen, right? The opening is 3/8 of an inch. All the material that was retained on the 1/2 inch screen above it would also be retained on the 3/8. That's why this makes sense, right? If the 200, which is the smallest sieve, if you only had a 200 sieve and you put your sample on that, you would damage the screen, but also everything above the 200 sieve would not go through it. So that's why this cumulative analysis works that way. Once the aggregate in the pan or the bottom of the stack is added, it should equal the weight of the initial sample, plus or minus a couple grams, right? There's always a little bit of dust making its way out. And the dustier your sample is, the more likely particles are going to go airborne, and you might lose a gram or two. So this table down here, let me turn on my laser pointer, is the way we write out a sieve analysis. So you can see on the left side here, we have the size of the sieves. And then someone, maybe it was you, maybe it was me, we went into the lab, we ran that agitation, and then we weighed each of these sieve sizes in a cumulative fashion. So in that 3/8 inch sieve, I see 0 stones, 0 weight was retained. On the number 4, we had 96.8 grams. So as someone who works with this a lot, I can tell you we're looking at a sand because there's not a lot of large particles, right? Nothing significantly larger than a number 4. And the thing is, all this keeps adding up down to 830. So we don't have 830 grams of dust. That was our sample size. We should have mentioned that 830 plus or minus was our original sample size. But so that is the data we get from the lab. We now have to do some calculations to figure out the percents, like I mentioned. The percent gives us just a more general understanding of the particle distribution. Looking at the weights, you kind of have to do the math out on your own. So that's why we do this math. Here's an example of the percent calculation we're going to do. For that number 4 sieve, if you remember, there was 96.8 grams, and we had a total of 830 grams. So we're just calculating a percent here, and I'll pull up a calculator so I can show you that the math on the screen is valid. So we've got our 96.8, and we're dividing it by 830. You can do 0.0 if you want, right? If you've got 0 as a decimal, you can take it or leave it when you're punching it into a calculator. And we're getting 0.11662650, on and on and on. When we're talking about percents, we report everything to the nearest 1/10 of a percent. So in this case, we're going to multiply that by 100 times 100, which is just moving that decimal place, right? We had 0.116626. We just moved the decimal over 2 places by multiplying it by 100, which gives us our actual, that's our percent. So we have 11.66%. And if you remember, oh, it's weird because that's not in the PowerPoint. My laser pointer shuts off. Hopefully you can see the pointer on my
Yep, we can.
Yeah. Cool. So if we're rounding to the 10th, we only look at the decimal place one to the right of it to round. We don't care what's happening over here. So we're looking at this number to see about rounding this one. And if it's 5 or up, we round up. If it's less than 5, we round down. Here we have 6. We're going to round that up to 7. That's where the 0.117 came from. We rounded it already in this example. So our answer then is 11.7% for this one sieve. Now we're just going to do this math. We go back here. That was 96.8, right? That's 11%. We're going to do this math over and over until we get to the bottom. So when we do that out, we're looking at 11.7, 46.2, 85.4, right? And that's just this number divided by the total, 830. And a good check on that is at the pan, 830 divided by 830 is 1, and that's 100%. And in practice, this might be 99.9, and that's probably going to be okay. You can look at your specs to see what the allowable variation is there, the allowable loss, but that should be as close to your original sample size as possible. And in the case of the difference here between the number 200 and the pan, right, this sample actually has very little dust, 0.4%. That's not a lot. That's good. So that is our first column of math that we filled in here, cumulative percent retained. We also describe these aggregates in, and most commonly describe it as percent passing. Now, the nice thing about cumulative percent retained and percent passing is they're opposites, meaning 100% minus 1 is the other. So if we know 1, we can go to the other just by subtracting it from 100. So we just calculated the cumulative percent retained. So to go to the other one, which happens to be percent passing here, we're just going to do 100 minus the answer we calculated for each of these columns, right? 100 minus 11.7, 100 minus 46.2, 100 minus 85.4, and so on. Now, if this weren't cumulative, if this were individual sieves retained, there'd be an extra step in between these to get to percent passing. So you have to make sure you're actually looking at cumulative percent retained, which in our class here, we'll always be discussing that way, but it is worth being aware of that. So here, the opposite, where we have 100% retained in the pan, that makes sense. The pan should catch our entire sample. Here we have 0% weight or 0 weight on the 3/8 sieve. That means 100% of our sample makes its way through there. So those are good kind of conceptual checks on what's actually happening with this test. And, you know, this math, I don't know how you feel about math. If it seems easy, that's a good thing. It's not meant to be exceptionally challenging, but the crazy thing is how important this type of test is for our built environment. So taking this type of test seriously and taking your time on it is really important. So that's why we're going to be practicing it. I think there are a couple questions in the quiz that go over some math here. The proper gradation ensures that the compacted mixture is going to resist traffic from damage. It's going to ensure we have proper coating of asphalt. If our asphalt content stays the same, but the gradation is changing, we're either going to have too much asphalt and cause a phenomenon known as bleeding, where the asphalt makes its way to the surface and reduces friction, becomes unsafe for the traveling public, or we don't have enough asphalt and particles are uncoated and the pavement breaks down quickly. So it's really kind of a sweet spot here that we have to be monitoring all these types of conditions. The gradations are checked multiple times per day on stockpiles, cold feed bins, and we're going to get into hut bins when we talk about plant production. They're checked there as well. The results of that gradation are used to make adjustments at the plant and monitor the quality of the mix. It's indicative of all of the quality. And for people who are working in the field, if our gradation is changing in a stockpile, there's no way they can be expected to get density and quality pavements when we're talking about placing it in the field. Jim mentioned earlier, recycled pavement. We recycle almost 100% of it. And there's a statistic, I should probably find a source for this. A long time ago, I heard that asphalt is the #1 recycled material in our country by weight because it's rocks. It's pretty heavy, right? We might recycle more plastic, maybe. Plastic's really controversial recycler, but it's not as heavy as rocks. So we get most recycled material in the country by weight. The way we recycle it primarily is by reincorporating it at a mix facility. We're talking about traditionally 15 to 20% of mixes going out of plants are blended, or mixes going out from plants are blended with 15 to 20% of that RAP. RAP is going to save money. It's going to help the environment. It's going to reduce costs and impact on that. Virgin is the terminology. So we're talking about materials that have come out of a quarry where we're taking it from the earth. So RAP is going to offset that. And it needs to be produced and managed properly, though. Looking at this gradation, right? If you go out and mill a roadway, what is the gradation in that roadway and how many layers are we milling through? And do those layers change all the time? So there's additional processing that goes on with RAP before it gets recycled, just crushing it down and making sure it's uniform before we end up mixing it back in, just so we can monitor and maintain the uniformity of the pavement better. So this is primarily how we get RAP. You've probably driven past one of these on a road or two. This is a cold milling machine. And what we're talking about here, the money-making operation is down in the belly between these tracks. It's a mandrel head with diamond impregnated tips that's actually going to crush up the road as it, or pulverizes is a better term. It pulverizes it as it travels over the road. These machines are really cool to be around. They're very impressive. Most of them have 2 engines, one to propel it and one to power the head, because it requires so much power to spin that head as it's grinding into the pavement. I mean, these can technically grind 4 to 8 inches. It's going to go slower the deeper you go. It's typically grinding about 2 inches off of a road as it travels. And then each of these tracks, which if anyone's watched the original Star Wars, I don't know if people do that still. It reminds me of the machine in the original A New Hope, where it's got those big tracks. But the point I was getting at is each of those can be adjusted individually, so you can actually change the grade or improve the grade and the cross slope of your road with these milling machines. This is a close-up of one of the heads, so you can see all these teeth. They're replaceable. After a long day of milling, someone actually has to go under that machine and inspect and replace these, make sure they're all in good working order. And if they wear out, you actually see a deficient product. So this big picture is showing you what a quality milled surface looks like. It almost looks like woven fabric, the way these teeth cut into the pavement. And that gives us a good, clean bond when we go and pave over it. It has to be swept. It has to be sometimes washed. They often will leave it open to traffic because cars going by, plus rain is going to help clean it off before we pave over them. But that is an image of a quality mill right there. The millings get hauled to a paving facility where they're going to be stockpiled and then reincorporated. As I mentioned, they're often crushed or separated into certain sizes, those aggregate sizes again, to make sure it's easier to get pavement produced more uniformly. So does anyone have any questions on that? I think we wrapped up a little earlier than last time, but we can do a couple more math examples if people feel like they need to.
I have a question, and I may have missed it. because they did step out, but do you guys have, you know, a formula for the kids to follow to do those calculations? Or a step-by-step kind of thing? I might be asking, they probably know everything and I don't.
No, no worries. I think we have a schematic that shows it. I will track that down and Erin can send it out later on.
That sounds perfect, thank you. Just so they can practice.
Yep, yep. The quiz is right, Jim. I haven't actually checked the quiz
Yeah.
myself, but I believe there are some practice problems in the quiz.
Yep, there are
And
some
we'll-
practice problems on the quiz. I was going to actually share that. I was going to share that and do one of the first
Okay.
calculations with them if
People have time.
yeah. Okay. So similar to the thing that Alex showed you, we give you kind of some cumulative weights here. And so the total weight of our sample is 444.4 grams. And so if we wanted to, we can take and we can figure out the percent retained on this first sieve by, so if we want to figure out the percent retained for this guy right here, it's just going to be 290.0.
You can also change it to where the T is. You can just type it in if that's easier for you.
Oh, why? Well, I've started
But
this
I
way,
do
but
like your writing.
my art skills are very bad, and doing this on a trackpad is even worse. Divide by 440.4, because that is our total sample size. And we're going to multiply that times 100. And that's going to give us
65 point, well, sorry, 0.6525.
so it
65.
becomes 0.65
6.5.
6525.
25.
Yep.
And then when we multiply that by 100, that becomes 65.25, but we're going to round that, so it's going to be 65.3%. So our percent retained here is going to be 65.3. You should see me with you should see me draw stick figures. It's even uglier. If that's possible. And then if we want to figure out our percent passing, what we're going to do is we're going to just come over here and we're going to take 100 minus our cumulative percent retained. So it's going to be minus 65.3, which is going to give us our percent passing is 34.7%. And we would repeat that for all of the different sizes that we have in that gradation. So for example, I just did question number 9. So if none of you should get number 9 wrong on the quiz.
We appreciate that demonstration, just having the formula and know the steps written. I think that's perfect. So thank you for taking the time to do that.
I also
think the
put
kids-
in the chat, we had written up very similar to what Jim did. It's like multiple pages of us doing this math out manually. So you can see each step of the way. It's in the chat, and I will re-email it to Erin so she can send it out too.
Oh, that's perfect. I will make that as a link today on the website where above the quiz.
And we realized too, like, you're learning new concepts as well as the math at the same time. So the first time you hear this, it might all seem a little weird. But the nice thing is, as a technician in this industry, you're going to do gradations over and over and over and over again, and you'll be able to do this in your sleep in a matter of years.
So that's, unless anybody has any questions, that's pretty much our presentation for today. It's a little bit better this way here. You guys aren't going to be quite so crammed getting to your next class. Aaron, do you have any, let me stop sharing my screen here. And anything from you?
I don't have anything. Like I said, Alex, if you email me that example, I will load that on the website as well as loading this week's video. And if anyone else has any questions,
We're always happy to answer questions.
okay. The quiz I will give you right now. Copy. It's also on our website, but I'll put it in the chat. That's the link to today's quiz. Again, it's also on our website. If anyone is joining us after this live video. And I think we're good. Thanks, everybody. We will see you next week.
Yes, thank you.
Erin, I'm
Thank you
sorry,
all.
Erin.
Yeah.
I'm interrupting. Do you think the kids will ever have an opportunity to do like a job shadow with these guys? Is that
Oh.
something possible?
I would think so. Oh, with Jim? Or with like
yeah.
Tilcon or,
Probably with you guys, because I think that's where most of the learning is happening. You know, they know what their job is and what they need to do, but I think it'd be really good for them
Well,
to see an action.
I know that we did a field trip the last time we did this program. We took a group to Tilcon. And they got to see the facility. They got to see pretty much the whole thing. But that's something we can definitely talk to Jeff about. And
Yeah,
Can
and
you
if
tell me where Hilton is, guys? Like what town?
oh, I'm not Jeff. He knows everything.
they have multiple locations throughout the state. So
Because we're geographically challenged, you know. We're way over, almost in Mass and Rhode Island, so I'll talk to
Right.
Jeff about it. Because
Yeah.
I think that would be really good for them to like learn, you know, as a final explanation for the job.
right. And if anybody would like to, if anybody wants to, we're happy to make arrangements at our lab to welcome anybody who would like to come to our lab. That's not a problem to spend some time there for a day or whatever. We have plenty of things going on, and we can show you all this stuff in person. That's not a problem at all. We would be most happy. We'd be most happy to do that. It's just the logistics of getting students there. That's always the challenge.
Okay, well, we can discuss and
Yeah.
try to make a plan for that. All right, thank you, everybody.
See you next week.
Have a great week.
Thanks, Erin.
Thank you.